Hello again, welcome back to another session. We are continuing with our atomic theory. We have now reached part 2. Remember, we learned a lot about more of the historical background leading to the modern atomic theory. So today we will talk about the important experiments that elucidated the substructure of the atom, that it is a divisible species, that we do have subcategories or subatomic particles. So I will let you know here what we will discuss today. So let's look at our agenda, our menu. Subatomic or fundamental particles, the discharge tube experiments, especially the cathode ray tube, canal ray tube, then the investigations of the behavior of these rays that were produced. What were their properties, magnetic or electrical properties? Could they be deflected in fields, etc.? Contributions by these famous people like Thomson, Goldstein or Goldstein, Chadwick, Millikan, etc. We will talk about the atomic model types in an overview quickly, and Rutherford's very important contribution of learning about the nuclear atom. Of course, all these people had a lot of help, and graduate students and research associates. These names are often not involved anymore, which is kind of sad, but the human being can only remember a few names, so that's why the main investigators are listed here, and these are the ones that became famous. Here we have Louis de Broglie, a French scientist who first studied the material waves, that small particles can behave like waves. J.J. Thomson, an English researcher or scientist, they were usually physicists or chemists or both, investigated the charge-mass ratio of the electron, which led to a later development of finding about the electron charge itself. Rutherford, you see here on the right, was very important for establishing the nuclear atom as a reality with his famous gold foil experiment. On the left we see here James Chadwick, who discovered the neutron, but that was much later because the neutron is a neutral species and couldn't be detected by the normal cathode ray type investigations using discharge tubes, etc. That was very important for the protons and electrons. So this was a little difficult to determine. The existence of the neutron, of course, escaped the scientists for a long time. So in the 30s, the neutron was also detected. But we'll see how as we go along. Now here we have an overview of the 3 fundamental properties that are so important for us chemists. Of course, the physicists will think, oh, this is laughable, we have many, many more particles. That is true. But for us chemists, these 3 particles are of essential importance. For instance, we have here the neutron, the proton, and the electron. So I'm sort of jumping the bat and telling you of what we have as our solid core knowledge today. The neutron has a mass of 1.67 times 10 to the negative 24 grams. This is practically 1 AMU, or atomic mass unit. Notice that the neutron and the proton have practically the same mass. There's a little tiny difference because the proton and the electron together would produce a neutron, or a neutron can decay into a proton and an electron. So the difference in mass is actually only the electrical or the electron mass, which is very interesting. But if we round the numbers to the nearest hundredths, they're practically the same. So we call this an atomic mass unit. So an atomic mass unit is always 1.67 times 10 to the negative 24 grams. So that's a constant mass. So when we talk about AMU, we mean this mass. So it's you can substitute one for the other. Now the electron is practically zero. It has a very small mass of 0.00, wait a minute, let me start again. 0.0009 times 10 to the 24 grams. Now the charge quantities are as follows. The neutron is zero. That's why the name neutron, neutral. And the proton is +1. And the electron is -1. So the charge quantity of these two fundamental particles is equivalent. They're the same. Even though the mass is completely different, but the charge quantity, the amount of charge per particle, is the same. Now this is very important. Here below we have the nuclide representation of carbon as the isotope 12. And we can see that carbon has an atomic number of 6, meaning 6 protons, and the mass number of 12. So mass number minus proton number or atomic number can easily give you the remaining neutrons. The neutrons can vary in number. That means this can lead to different isotopes. Isotopes are species of the same element with the same atomic number, which characterizes the element, but different neutron number. Because a neutron number, as a nucleon, doesn't get involved with any charge balance effects. So we have the electroneutrality principle, where the number of protons has to be equal to the number of electrons for the neutral atom. The neutrons can vary, as I mentioned already, and this leads to the phenomenon of isotope individuals. So here we have two isotopes, carbon-12 and carbon-14. So 14 minus 6 gives us 8 neutrons, and here 12 minus 6 gives us 6 neutrons. So the lighter isotope has 12 AMUs, or if we want the absolute actual mass, we would have to multiply this coefficient 12 times what the AMU represents, which is 1.67 times 10 to the negative 24. And the carbon-14 has 14 AMUs. So 14 is the coefficient. It's just an integer. And the unit would be AMU. And if you really want a substantial unit, you just have to substitute AMU, the AMU for the actual value of one mass unit. And then 14 times 1.67 times 10 to the negative 24 grams will give you the real mass of that particular atom. This is what we call the nuclide representation, where we only show the atomic number and the mass number to illustrate isotope, different isotopes. Now let's start and talk about the important experiments. Now the first one is the cathode ray tube that was very handy in doing various experiments. It was actually essential in the development of the modern theory of the atom, leading all the way to the quantum mechanical model. So let's thank the cathode ray tube. It's a glass body similar to what I'm showing you here. I'll show you this again. This is a little modified cathode ray tube. We'll see the significance in a moment. The electron path is produced by two electrodes that are fused into the glass. And we have here a valve that allows us to get rid of the air inside, which is always there in any container. We have to evacuate and then maybe introduce some filler gas material, such as hydrogen. We want only a semi-vacuum, because a total vacuum would not produce any visible beams or rays. So we fill in a little bit of hydrogen here, which is the smallest element. It's a one electron system, as we have finally realized. So we have here a current, high potential, which allows the electrons to step out of the cathode material. The cathode is the negative electrode because it provides the electrons, and the particles that move to the cathode are usually called cations. So the cathode is the electron donor electrode, and once the electrons step out, and we have a high current, then the potential difference is so high that these electrons will be accelerated towards the anode on the other side, which absorbs these electrons, so they flow through the system, so the cycle is closed. Now what is interesting is that we see a beam of light. And this is actually, as it turned out to be, a beam of electrons. That's why we call these cathode rays that are produced in the cathode ray tube cathode rays. At first they didn't know it was consisting of electrons, but some experiments were done that showed that these rays could be deflected in two types of fields, the electric field and the magnetic field. Now first of all, I want to just tell you a little bit of what we know today. This wasn't known at the start, but the fast cathode electrons bombard the hydrogen atoms and knock off an electron. This is what we call ionization. So we have a separation of the charge. We have the protons left over in the so-called nucleus, and the electrons are also accelerated towards the anode, just like with the other cathode electrons. And occasionally, or quite often actually, because of the high energy of these electrons, they might recombine with a residual ion, a proton, and this would lead then to the production of light. So the recombination of the protons with an electron is the phenomenon that we observe. So that is what we now know. These cathode ray tubes were often also called Crookes tube. They were called Crookes tube because Crookes was a very famous scientist in the British Isles who developed these glass tubes a lot. In Germany they were called differently. They were called Brown tubes. So everywhere in the world somebody experimented, but you couldn't keep track of everybody. It depends also who published first. Well, anyway, this is the Crookes tube or cathode ray tube, which was subjected to outside influences. The rays were then observed to be deflected by an outside electric field in the direction of the positive electrode. Now what does that tell us? The positive condenser plate, we should say here, that produces an outside electrical field. What should we say here about the cathode ray characteristics? They must be negative because we know that opposite charges attract and like charges repel. So we could bend the rays in its path by virtue of the outside electric field. Now the same thing was carried out with the magnet, So we have field lines here between the two arms of the U-shaped magnet or horseshoe magnet, and by putting a little slit in between the cathode rays and the anode and the magnet, we could get a smaller beam, and we noticed that the beam was dropping downward because of the field, magnetic field. Remember, when there are electrons, they produce, in a sense, a current. And if the magnetic field is in the direction of the thumb, the electrical current in direction of my forefinger, and then the mechanical thrust of the beam would be pushed downward. This is the three-finger rule. So that means we understand that the beam also has magnetic properties as an electric flux. So this is already extremely interesting. That's a lot of information that we can deal with. Now, let's talk about the next interesting phenomenon, the properties of the cathode rays as a particle, because the cathode rays can be considered to have particle characteristics and wave characteristics. So let's look and see how they behave. And let me find this here in my here we are. Sorry, this is a little bit different from what I'm showing, but that will be clarified. So we see here in our PowerPoint slide the two cathode ray tubes that will be used to test different phenomena. On the left we have a little pinwheel adjusted between the two electrodes. And then one observes that the pinwheel rotates. So it's like a little windmill, and that can only rotate if particles hit it. Now in the atmosphere, it's the air particles that would bombard into the wheels or the blades of the propeller or windmill or what we might be using. So a pinwheel is a little thing that can rotate when the cathode ray tubes, cathode rays hit these blades of the pinwheel. So it rotates, and that's an indication that we have particles involved. On the other hand, on the right, we see here the cathode rays going through a tubular anode, so you can always modify these electrodes, you can modify the tubes for any experiment that you might want to carry out. And so the tubular anode allows the cathode rays to go through, fly right through, and if we have a little impediment here, an image like a little flower or whatever you might use, they use sort of a cross in the original experiment, it would produce a shadow. And that is certainly a characteristic of waves, of electromagnetic waves or light. Producing a shadow means that the rays behave like light and illuminate every area that is not going through a solid object. Next, we would like to talk about the experiment that was carried out by Thomson in England. This was all carried out more or less around the turn of the century, from the 19th to the 20th century. So at the end of the 19th century and the beginning of the 20th century. Things happened very fast. Many scientists knew each other, they worked in each other's laboratories, they communicated, so it was really a cohesive effort. Now let's look at this tube. This is a modified cathode ray tube. We have here our cathode at the end and our tubular anode, and we produce a nice thin beam of cathode rays. And now we use two fields. We use an electrical field and a magnetic field, which are perpendicular. And then what Thomson did, he focused the beam to the middle. So he compensated for the electrical and the magnetic field, and then he read off the numbers on his calibrating platform, and then he could establish the electrical or the mass or charge to mass ratio of the electron. So that's an EM ratio, and that was very important. At least you got some kind of numerical data, although you could neither determine the individual charge or the mass of the electron. So you see we're moving in and getting more information about the electron by these experiments. Next, a very interesting experiment was carried out by Millikan, an American scientist. And this is the so-called oil drop experiment. The oil drop experiment was ingeniously devised. It was a container with two condenser plates. We have here the positive plate and the negative plate below. An X-ray source was used to ionize the hydrogen gas inside, the container. We have an atomizer here that produces a very, very fine mist of oil, mineral oil. I don't think they use salad oil or olive oil. So it was atomized, meaning not produced, not changed into actual atoms, but very, very fine little miniature droplets. So a mist of oil. The cathode condenser part had a little perforation in it, a hole through which the oil drops could fall. And as they fell down, they picked up, normally gravity would let them go to the bottom, gravitational force would lead them to the lower level. It's not only charge, but also the pull of the gravitational acceleration that would lead the oil drops downward. But what could prevent them to go down was picking up, like a landing site, little stray electrons that were produced by the X-ray ionization process, which we see here in that little equation. So the electrons could land on an oil drop, either as one electron or two electrons or three electrons or any multiple of electrons. Now what the observer did here with his little telescope looking through was to calibrate the countercharge so that the oil drop would remain suspended. And when that happened, this person would record the value. And it turned out in the end that when both forces were in equilibrium, that we have a multiple of this value. So this smallest multiple of this would be actually the ultimate charge of the electron. So that was fantastic. That means with this charge, and it was 1.60 times 10 to the negative 19 Coulomb, which is a unit of charge. And with this and the EM ratio, we could determine the mass of the electron. So that is the end of that story for now. Then we go on and check out protons. Protons were discovered a little bit later than all this. And here again, we used a modified cathode ray tube. And this one I'll show you here in more detail. Here we have the canal ray tube, because the rays produced are called now canal rays. Oops, have to find this. Here we are. So this is my canal ray tube, and you see how it's perforated? So we have a tubular anode in here. No, it's not quite a tubular. It's just attached. So the cathode is perforated, the anode is on the other side. So that means the cathode rays would go in this direction, and the canal rays would fly right through the cathode, because they are positive, so they'll be attracted to the negatively charged cathode. So the beams are coming on the other side. You can do the same tricks with these canal rays, as we call them, because they're like little canals, you could say. They're going through little canals or perforations, holes. So these canal rays can also be tested for the deflection in electrical and magnetic fields. So they'll be behaving oppositely to the electron rays. They would be attracted as positive rays to the negative plate, condenser plate, and the other, they'll be deflected upwards in the magnetic field and so on. You could also do an EM ratio with them. So you could do the same experiments. This canal ray experiment was carried out by Goldstein in Vienna. Oops, no, not in Vienna. This other person is Wien. So in 1886, they found out the mass of the proton with the help of these experiments. It was 1.67261 times 10 to the negative 24 grams. So actually what we had before, 167 times 10 to the negative 24. So we got that. And now, last not least, we're looking for the neutron. And take a little quantum leap in time. In the 1930s, actually in 1932, James Chadwick did a very interesting experiment. They did a lot of experiments in those days with X-rays or bombardment experiments of alpha particles on different source material, different targets. So what was happening here is that beryllium, a beryllium isotope 9, was bombarded with alpha particles. And remember, alpha particles are just helium nuclei. They come from a natural radioactive source, and fast movement of these particles collide with these target atoms, and something happens. The internal nucleus is disrupted a little bit or shaken up, let's say, and we get two new particles coming out. And this is well, first of all, we get the carbon-13 as an intermediate, which is very unstable. It's a very unstable isotope of carbon. The stable one is carbon-12, and another one is carbon-14, which is less stable but not that unstable as carbon-13. And then it stabilizes itself by shooting off a neutron, and as a result we have that stable carbon-12. And this neutron, now how are you going to detect it? Because it's neutral, it's evasive. So the trick was to use a Wilson cloud chamber. This is a wonderful device. I don't want to get into that too much, but it uses the condensation nuclei property of attracting moisture. So when you think of the path of neutrons as a condensation trail, when alcohol molecules or water molecules supersaturated in a supersaturated chamber will start collecting around these particles, then you can make them visible. And that is the case that was in our experiment here. Last not least, we like to talk about the nuclear atom and Rutherford's experiment. And time is running short, so I will carry that over to section 3. Thank you.